Hi all, this video is on replacement models of capital items that consider time value for money, and you also have the salvage cost included, which is slightly different from the previous problem that we had solved in the series 5.2. So you could have a look at the previous example to see what difference this problem makes in comparison to the previous one. So this problem, as I had mentioned, is about the replacement of the capital item while considering both running costs and the salvage costs. Now, in case you've not subscribed to this channel yet, please do subscribe and also click the notifications button. So as and when I post my videos, you will also be notified. Thank you, and also feel free to send me your comments either through email. The email is here. My personal Gmail ID is what I would prefer to have your comments in. And you would also do me a lot of favor if you put your comments and your likes in my channel. And if you do have something of concern that you would like me to change or correct, please feel free to let me know. And here we get into this problem. Yeah, you can have a look at this problem. As I always recommend, do take a screen snapshot of this problem and copy down the problem in your notebooks. It always helps to solve the problem on your own, and practice is what makes one perfect. So have a look at this problem. The cost of the machine is 6,000 rupees and running cost has been mentioned for 7 years. Resale value is mentioned for 7 years, and the interest rate is 10% per year, which is the value of R. Now in the previous video, which is QTDM 5.2, in which we had solved a problem considering the time value of money, we had also mentioned that when we are doing the discount factor on the running cost, it is always n minus 1. That is, in the formula, it is 1 divided by 1 plus r by 100 to the power of n minus 1 if it is running cost that we are trying to discount, and if it is the salvage value, then it is 1 divided by 1 plus r by 100 to the power of n. The reasons and the justification of why we do this have been mentioned in the previous video. So in case you've missed out seeing the previous video, please do go have a look at replacement models QTDM 5.2, which is there in this channel. Now, having gone through the problem, let's get into the solution part. Now, as always, I try to remove the table values. Okay, having removed all these values, now I'm not too sure if you're wondering why I left these values alone. If you have a look at it, the data that we have is here, then running cost and the salvage value or the resale costs. The resale value rather than calling them cost, so we'll call it as resale value or the scrap value. So here you find 7 years is the first column in the table, and then the running cost has been mentioned here. This is as per the data given in the problem, and then the sixth column is about the scrap cost here. All these three columns are what we have in this data table here, so nothing that we had computed. So now if you find, I told you the running cost is always discounted with n minus 1, and in the formula, which is 1 divided by 1 plus r by 100 to the power of n minus 1. So if n is 1 here, then in the formula it would be 1 divided by 1 plus r by 100 to the power of 1 minus 1. R is 10%, so it is 1 divided by 1.1, which is again raised to the power of 0. and for the second year n value is 2, and what happens here is 1 divided by 1 plus r by 100 to the power of 2 minus 1, so that's 1. 1 divided by 1.1, it should be around 0.9091. It's actually 0.9091, which is 1 divided by 1.1. And for the third year, it should be 1 divided by 1 plus r by 100 to the power of 3 minus 1, which is 1 divided by 1.1 raised to the power of 2. So it's 1 divided by 1.21, which could be around 0.8326 and so on. So we calculate the discount factor with that formula of 1 divided by 1 plus r by 100 to the power of n minus 1. This is for the running costs. So if we do these calculations, I think this is what we should be having. So have a look at this. So this is what we have here. The first year's discount factor is 1, so the second year it is 0.9091, and then 0.83 or 0.8265 and so on. Now the third column is about the discounted running cost, which is running cost multiplied by the discount factor. So this is going to be 1200, this is 1400 into 0.9091 and so on. Now if we do that, we should be getting these values. Okay, and like in the previous problems, we always calculated the cumulative discounted running cost, which is 1200 comes here, then 1200 plus 1272, and then this value plus 1322, then this cumulative value plus 1352 and so on. So if we do that, we should be having these values. So 1200 is the first row, 1200 plus 1272 makes it 2472 plus 1322 makes it 3795 and so on. Now we have got the cumulative discounted running cost. Now we come to the scrap value. This is again as per the data given. We should be discounting the scrap value also. In order to discount the scrap value if required, you can have another column which is 6A, which is between the 6th and the 7th column. That column, which would be 6A, would be the discount factor for the scrap value or scrap cost. Okay, let's call it as scrap value. Now 6A, as I told you, would be the discount factor for scrap value, and I also said the discount factor for scrap value is calculated based upon 1 divided by 1 plus r by 100 to the power of n, unlike n minus 1 that was used for running cost. So when we have 1 divided by 1 plus r by 100 to the power of n, the second year discount factor of the running cost would be the first year discount factor of the scrap value. So if I have another column 6A, this would be 0.9091 for the first year, 0.8265 for the second year, 0.7513 for the third year and so on. But because I don't have the column included here, if you need, you can do that, and that could make your calculations a lot simpler. But here what I do is I multiply this 0.9091 by 4000 because it's just a shift up. 0.8265 into 0.7513 into 2000, 0.683 into 1500 and so on. So if we do that, we should be having this as a scrap value which is discounted. So 4000 multiplied by 0.9091 would have been 3636, and 2666 multiplied by 0.8265 would have been 2203. Alright, so we have the discounted running cost, we have the discounted scrap value. Now in all problems that had time value of money considered, we know we don't divide the total cost by the year, but we divide it by the cumulative discount factor. Now here we do the cumulative discount factor based upon the discount factor of the running cost. So here it would be 1, then 1.9091, then 1.9091 plus 0.8265, and so on. So if we have a look at it, then this is what we should be having. So have a look at this. This is what we have, the cumulative discount factor. Now for the total cost, this is the capital cost, which is 6,000 rupees, minus the discounted scrap value, which is column 7, plus the discounted running cost, which is column 4. So in other words, capital cost 6,000 minus the discounted scrap value plus the discounted running cost. So if we need to look at this here, this should be 6,000 minus 3636 plus 1,200. So that is 7,200 minus 3636. So likewise, for every row, it's the capital cost minus a corresponding discounted scrap value plus the corresponding discounted running cost. If we do that, we should be having this. So check this out. So this should be 6,000 being our capital cost. Yeah, 6,000 being the capital cost. 6,000 minus 3636 plus 1,200. I hope you get this answer. And then finally, the average cost would be the total cost divided by the cumulative discount factor. So this is 3563 because the discount factor here is 1. And here it is 6269 divided by 1.9091, 8292 divided by 2.73, 10122 divided by 3.4869, and so on. Now if you do that, you should be having your values back here. I've removed the decimals and held on only to the integer values here. So you have a look at this. The costs are decreasing till about the end of the 6th year, and it begins to increase from the 7th year onwards. So we take a call to replace the machine at the end of the 6th year. Between the 5th and the 6th year, it's probably constant. If I include the decimal values, then there could be a slight difference. But in a capital item, the decimal values don't make much of a significant difference, so we don't consider that here. So in this case, we take a call to replace the machine at the end of the 6th year. So this would almost bring us to the close of replacement of capital items with considering time value of money and without the time value of money being considered. You could also probably take down this problem for your practice. You can take a screen snapshot and probably copy this problem down. The answer is you replace the machine at the end of the 5th year. Okay, so we stop here for the moment, and the next video would come up relating to the replacement of small items. Thank you.